Welcome to the mass spectra of elements video. By the end of this video, you should be able to explain how isotopes of an element differ from one another. You should be able to explain how mass spectrometry can be used to determine the mass and abundance of isotopes in a sample. And you should be able to calculate average atomic mass using mass spec data. So isotopes are atoms of an element with a different number of neutrons. And because neutrons comprise a large portion of the mass of an atom, that also means that they'll have different atomic weights or different atomic masses from one another. Take hydrogen, for instance. Hydrogen exists in 3 naturally occurring isotopes. The first, which we generally refer to as hydrogen, it's the most abundant, has 1 proton and no neutrons. The second, deuterium, which is a little less common in nature, has 1 proton and 1 neutron. Therefore, it will be heavier. Tritium, which is pretty rare in nature, has 1 proton and 2 neutrons, which again will be heavier. Notice that in each case, there's 1 proton. Therefore, the atom is hydrogen in each case. However, its mass will be different because it has a different number of neutrons. We can determine the mass of individual atoms in a sample using a mass spectrometer. It does this by separating the atoms in a sample by mass. So for instance, if I were to inject a sample of hydrogen into a mass spectrometer, it could separate out the 3 isotopes based on their mass and then record what percentage of that sample is each isotope. It does this in just 4 general steps. First, when you inject the sample, it's ionized, meaning it's turned into ions. From there, it's accelerated, meaning it's just generally sped up. Here's where the separation occurs. The device uses a series of magnets here to deflect the sample. So as you may know, or kind of commonsensically, heavier atoms will, or ions in this case, heavier ions will deflect less than lighter ions. So you can see the degree of deflection is different for different masses here. So the lighter ones will deflect a little bit more, and the heavier ones will deflect a little bit less. And then finally, there's a detector which measures what percentage of the sample was made up of each isotope. When you get a readout from a mass spectrometer, it looks like this. So you'll see here, this is a sample of zirconium, which is made up of 1, 2, 3, 4, 5 different isotopes. You'll see that this sample, 50% of this sample was made up of zirconium-90, meaning zirconium with a mass of 90. Juxtapose that to these other isotopes, which are much less abundant. For instance, zirconium-92, only about 18-ish% of the sample was made up of zirconium-92. Another example of a mass spectrum readout. Pause the video here and take a look at the periodic table and see if you can figure out what element this mass spectrum readout is for. Welcome back. Notice that 75% of this sample is made up of an isotope with a mass of 35. Looking at the periodic table, we can assume that this is a mass spectrum readout for chlorine because chlorine has a molar mass of 35.45 AMUs, meaning that most of the sample has a mass of 35. Notice that chlorine does have a second isotope, which is a little bit heavier, which is what accounts for the fact that its average atomic mass is a little bit more than 35. The average atomic mass of atoms in an element can be calculated using the relative abundance of the isotopes in the naturally occurring sample. The value you get when you do this should be the value that you find on the periodic table. The periodic table values represent the weighted average of all of the isotopes in a naturally occurring sample. The equation we use to calculate this looks like this. This is just a weighted average equation. So the average atomic mass is going to be equal to the abundance of the first isotope times its mass, plus the abundance of the second isotope times its mass, plus the abundance of any additional isotopes times their masses. So if you're dealing with a sample with only 2 isotopes, you would do this for each isotope. If you had more, you could add an A3 times M3, and so on and so forth for however many isotopes you need. The math here is pretty straightforward, but the thing you need to be cautious of is to make sure that you convert your percents to decimals. Notice that often on the previous slide when we saw the mass spec readout, It had values in percentages. You need to convert those to decimals in order for this to work. It should be pretty obvious if you forget to do that because you'll get an absurdly large value. It's always important to reality check your answer when you're done. So let's go ahead and calculate the average atomic mass of chlorine from the mass spec data that we looked at before. So here you see the mass spectrum. It has about 75% of the first isotope with a mass of 35-ish, and about 24% of that sample has a mass of 37. Remember, we're going to use this equation. Since we only have 2 isotopes, we only need these 2 terms here. So let's go ahead and do this math. So our average atomic mass is going to be equal to the mass of the first isotope, which is 34.97, times the abundance of the first isotope. Remember, this must be converted to a decimal, otherwise you'll get an absurdly large answer. And we're going to add that to the mass of the second isotope times its abundance converted to a decimal. Simplify this, and you should get 26.5 for this first term, plus 8.98 for the second term. Add those together, and you get 35.45 grams, or 35.45 AMUs. You can reality check this answer, right? So notice that our 2 isotopes both have a mass around 35, so our answer should be around 35. If you don't get an answer around 35, you've done something wrong. Furthermore, it should be closer to the more abundant isotope. In this case, it is. And you can further check that by going to the periodic table and seeing if the mass that you got matches what the periodic table tells us. That brings us to the end of this video. Let's review our goals. First, we looked at how isotopes of an element differ from one another. Recall they have different numbers of neutrons and therefore different masses. Then we used mass spectrometry. Then we looked at how mass spectrometry can be used to determine the mass mass and abundance of isotopes in a sample. And then we used mass spec data to calculate average atomic mass.